In this experiment, we'll be looking at intermolecular forces as a predictor of the physical properties of several different liquid solvents. And so what we're essentially trying to do is make a connection between the chemical structure of a compound and the physical properties that we observe when we examine these compounds on a larger scale. So we can look at, down to individual molecules, how they interact with each other, and that can help us to explain why we see some of the properties that we see when we have an entire flask of this substance. And so let's think for a minute about the thermodynamics involved in state changes, because we're mainly going to be looking at evaporation, which is a change from liquid to gas. So let's imagine we have a beaker full of a liquid, and in a liquid, the particles of the compound are pretty close together and not allowed to really move that freely. It's a bit more free than a solid, for example, but still they are confined to a particular volume. When you actually change the liquid substance into a gas, they have a lot more freedom and can move around in a much larger volume and have more space between particles and move much quicker. So based on our understanding of entropy as a driving force for processes, it would be much more favorable, entropically speaking, for a substance to go from a liquid to a gas. But we also see very frequently in the world around us that gas is condensed down to liquids. And so what is it that drives this process? That is best explained by the other term of thermodynamics, which is enthalpy. And the enthalpy involved in this is essentially the attraction between the particles to help them be able to get closer together. And so we can't ignore this. It's a very important force involved in a substance, and these attractions are the intermolecular forces. They're attractions between different molecules, and that's what the intra part is referring to, the between separate molecules. And so this is directly related to observations we can make of the temperature at which different liquids will boil, and also directly related to the temperatures at which we will observe different solids melting. So as you have more intermolecular forces, the temperature of boiling or melting, I'll write B and M for those, would typically be higher because there's more forces that have to be disrupted, so more energy input is needed in order to cause those state changes to occur. So if we think about three substances that we're pretty familiar with from daily life, carbon dioxide, water, and sugar, these each have different states. So carbon dioxide we know to be a gas at room temperature, water we know to be a liquid at room temperature, and sugar we know to be a solid. And so these three substances must have pretty different intermolecular forces relative to one another in order for this trend to exist. Water is an interesting example, though, so let's not go 100% on this. Water does have hydrogen bonding, which is our strongest intermolecular force, but the spacing between water molecules in a liquid is actually a bit smaller, so that actually allows it to be a liquid at a larger temperature range than most other substances, so that's kind of an exception. But we could generally say that between these three, we'd observe an increase in the intermolecular forces as we move toward the more solid substance at room temperature. So this sugar should have the most intermolecular forces, and if we were to look at it, there are a lot of dipole-dipole forces in sugar molecules because of the number of oxygens and the structure. But carbon dioxide is a symmetrical molecule, And so there's no, the dipoles cancel each other out, so there's not really an overall dipole of the molecule, so we end up with just London dispersion forces being the primary IMF. So we could say this has the least strong intermolecular forces, the number of intermolecular forces, as well as the strength of the intermolecular forces is going to be key in determining these kind of properties. So the research question that we're focusing on in this experiment is, do the macroscopic properties that we observe depend on the strength of the intermolecular forces? And so you will compare as a class measurements that are made for 6 different solvents. Each group is going to examine a different solvent, and I put this as a note here that solvents imply that at room temperature they're liquids, so they're relatively similar properties at room temperature to be able to compare them. And so one of the first things you'll have to do is actually make predictions about what you might observe based on the molecular structure. So if our research question is going to come out to a positive, yes, the macroscopic properties do depend on the strength of intermolecular forces, then the predictions that we make in the beginning should be pretty close to what we actually observe as far as trends go. All right, so I'm giving a couple of example structures here. So in the first structure, we have just CH bonds, and we have a 4 kind of carbon chain here. This is a butane molecule. There are no real dipoles here because the electronegativity differences between carbon and hydrogen are so small that they're considered essentially negligible for this kind of structure. And so the main intermolecular force we would see here is London dispersion forces. If we look at the next molecule, which is ethyl acetate, we have a lot of the CH3 kind of groups, so those are more like London dispersion forces in those areas of the molecule. However, we do have carbon and oxygen bonds, which are both polar bonds. So we could think about the little dipole that comes from this carbon-oxygen bond, and there's also a dipole that comes from this carbon-oxygen double bond, and that one is actually a bit stronger. So if we were to figure out the overall dipole, it's more in this direction. So that means that we would have a dipole-dipole IMF as the main intermolecular force for this molecule. We would also see that in the last structure for acetone, that the dipole between the carbon and oxygen leads to a dipole-dipole IMF prediction. And so how would we compare the two of these to one another if their main intermolecular force is dipole-dipole? Well, we could also think about the fact that there are more opportunities for London dispersion forces in a larger molecule. So the size and surface area of a molecule are actually going to come into play in our consideration. So a larger molecule, we would expect to have more London dispersion forces, which I'll just call LD here, compared to a smaller molecule like acetone. So I'll say, so we would expect, based on this, that the weakest interactions are going to be for the butane that we already saw only has London dispersion forces, and the strongest intermolecular forces are going to be for our ethyl acetate that we already examined, that has more London dispersion forces than acetone, but it also has dipole-dipole. So if we were to make predictions about the properties, then if something has weak intermolecular forces, going back to our same logic here, the enthalpy is not as great for the substance to stay in the liquid state. So it will be easier for it to turn into a gas. And so we could say that it will likely evaporate quickly. And we could say the opposite for something that has more interactions. It's more likely to stay in the liquid phase longer. So the evaporation rate for something with strong intermolecular forces should be slow. And then we would observe, hopefully, the acetone somewhere in the middle in terms of the rate. So once you have actually made some observations, you'll have values that you can compare, such as times, temperatures, and so on. As a class, you'll bring together all of your data for the 6 different solvents and be able to see whether your predictions held true and address your research question in a group argumentation session.